So today we're going to start a little bit with chapter 3, and then we're going to skip over to chapter 5. And this is ambitious. I don't know if I'll cover all of this on chapter 5 today, but just a little. And then on Wednesday, be prepared. The first 15 minutes of class on Wednesday, we're going to have an in-class quiz. That means it's not for a grade, but it is an in-class quiz at the beginning of the lesson. Have your periodic table and your calculator handy for that in-class quiz. We're going to be needing those today also. So I hope you've got your periodic table and your calculators handy. Let's get started. Okay. There's this wonderful concept in chemistry called the mole. And the mole is a counting number. And if you have a mole of anything, that is equivalent to this many items. It's equivalent to 6.02 times 10 to the 23rd items. This right here is referred to as Avogadro's number. Avogadro's number. And the reason it's referred to as Avogadro's number is because there was a scientist, Amedeo Avogadro, who determined this to be a very important value. He determined that to be a very important value. And what we found out is that if you have 6.02 times 10 to the 23rd atoms, you have 1 mole of atoms. In fact, the definition of what is a mole, the actual definition, is actually the number of carbon-12 atoms in exactly 12.0 grams of carbon-12. That's the actual definition of what is a mole. But how many atoms you have in exactly 12 grams of carbon-12. And it turns out to be this number, 6.02 times 10 to the 23rd. Now, if this number just seems so outrageous, remember that we do know some other counting numbers. Like, for example, if I was to ask you how many items in a dozen, well, you'd probably tell me 12. If I was to ask you if you had a gross, like a gross of pencils, you'd tell me, well, that's 12 dozens or 144. So you are familiar with this idea of counting numbers. It's just that this is such a large number, it seems kind of unusual to us. But I want you to think of a mole kind of like we think of a dozen or a gross. It's just a lot more items. Now, the usefulness of a mole is because we cannot count out individual atoms. It's impossible to count out individual atoms. I couldn't ask you to bring me a dozen carbon atoms. I couldn't ask you to bring me a gross dozen atoms, but I can ask you to bring me a mole of carbon atoms, because it turns out that there's a relationship between the mole number and what we call the molar mass. The molar mass of an element, that is the mass of that element in grams. And that is equivalent to Avogadro's number of those atoms. So for example, oh, hold on, I forgot to put my light up. I just realized now. So the molar mass of an element is its mass, but in grams. And it's going to be equal to the mass of 1 mole of those atoms. So for example, the molar mass, and we've already done this one, but we'll do it again, of carbon is equal to 12.00 grams. That is equivalent to 1 mole of carbon atoms, or that's equivalent to Avogadro's number. Now, if you're wondering where I'm getting that value, I'm getting it from the periodic table. We'll try others here. The molar mass of sodium. Sodium's number 11. I'm going to round it, 23 grams, and that's equal to 6.02 times 10 to the 23rd sodium atoms. One more just for fun. We'll pick sulfur. And it has a mass of 32.06 grams. And that again is equivalent to that many sulfur atoms. So what I'm doing here on this number, that from the periodic table is the atomic mass. But if I was going to do atomic mass, it would be 32.06 atomic mass units. But if I want molar mass, I change it to grams. So if you're wondering what's the difference between that and atomic mass, you're right, it's the same number, but different units. So how many times have you heard me say units matter? Okay, units matter. So for molar mass, make sure that you write the unit of grams after the atomic number. Always, always, always. Now we can also do the molar mass of a compound. And that's simply going to be the sum of all of those atomic masses in grams. So we'll start out with something simple like water. The molar mass of water, well, you've got 2 hydrogens, which are 1 apiece, and then you've got 1 oxygen, which weighs 16. So the molar mass of hydrogen is 18 grams. And that would be the mass of this many molecules. Or you could say that is the molar mass of 1 mole of water. So if we try another one, let's say oxygen gas. Well, oxygen gas has 2 oxygen atoms. Each weighs 16. So 1 mole of oxygen gas is equal to 32 grams. That's the molar mass of oxygen gas. That means if you have 6.02 times 10 to the 23rd molecules, they will have a mass of 32 grams. So far, so good.
Can you move up your paper?
Can I move it up?
Yes. Thank you.
So if we're doing okay, would you type in a number 1 into the chat window for me? A number 1. All right, good. So I think everyone's with me so far. So far. Now we're going to do a little bit of converting. Okay, let's do a little bit of converting. So we'll take water because it's a simple one again. We know that 1 mole of water, 1 mole of water is 18 grams. Well, what would be the mass of, let's say, 27.5 moles of water? What would be the mass of that? So I'm asking for my answer to be in grams. So I'm going to take this and I'm going to make a conversion unit out of it. I can do 1 mole over 18 grams, or I can do 18 over 1 mole. Okay, that's my conversion unit for the molar mass of water. So now I'm going to start with what's given. And the given is I want to have 27.5 moles of water. So I'm going to multiply this by one of my 2 conversion units. And remember, you always want to keep what's on top. So if I'm trying to figure out what the mass of something is, I'm going to put the unit with grams on top and moles on the bottom. So if 1 mole weighs 18 grams, then 27.5 of them, I'm just going to multiply 27.5 times 18 grams, and that will tell me the mass of 27.5 grams of water, which when I get the answer is 495 grams, which by the way is about one of those 20-ounce water bottles. That's almost 27.5 grams of, or 27.5 moles of water. We'll try another one. What is the mass of, let's say, 15.2 moles of water? Same thing, start with what you have times your conversion factor, (273.6 grams). And now we can go the other direction. We can go the other direction. You have 502.1 grams of water. How many moles does that represent? Well, go the other direction. Start with what you have times 1 mole over 18. And that would be about 27.9 moles of water. So converting between moles and grams, that's something we're going to be doing a lot throughout the semester. We're also going to do it a little bit when we start doing our gas laws on Wednesday, but I wanted to introduce the idea of what is a mole today. And remember that a mole is a counting number. A mole is a counting number. It would be difficult to count out for me this many molecules of water. If I had a recipe and I needed exactly 27.9 moles of water, that would be difficult to count out. However, you could count out 502 grams because 1 mole of water weighs 1 ml, so you could easily bring me this much water. But if you know the relationship between the mass and the number of moles, most of the time when we measure out how many moles we need, we do it by mass. That's what we typically do in the chemistry lab. We cannot count out this many, because remember, 1 mole is that 6.02 times 10 to the 23rd. I can't count that out once, much less almost 28 more times. But I can weigh out on a balance a little over 500 grams. I can do that. And if the balance says this much, then I know I have that many moles of water. So the usefulness of moles is it allows us to count out the number of individual atoms or the number of individual molecules or the number of formula units that we need of something, but we don't have to count them out one by one. We count them out by measuring them on the balance. That's the usefulness. Let's practice with a couple of more and then we'll move on. So work on these for me real quick. I want to know, following, okay? Solve the following. If you have 2.5 moles of this chyme sodium chloride, how many grams is that going to be? And if you have 1.4 moles of, let's say, calcium fluoride, how many grams is that going to be? 2 more. What if you have 126.2 grams of magnesium sulfide? How many moles do you have? And if you have 85.5 grams of lithium bromide, how many moles of that? Okay. Remember, for each one of these, the first thing you need to do is to determine the molar mass. In other words, 1 mole of that compound equals how many grams? So for each one of these, that's the first thing that you need to determine. I'll give you about, 5-10 minutes to do this. So here are the solutions. Remember that I'll put these up on Blackboard and you can download them. But let's jump over to chapter 5. And now we're going to talk a little bit about gas laws. Let's step over to chapter 5. Well, when we measure gases, well, just as kind of a reminder, it's been a while since we've talked about like the properties of the gases, but we'll go ahead and we'll list them real quick so we can kind of put our mind back into thinking about gases. But when we talk about properties of gases, one of the properties that they have is that their particles are far apart. Okay, there's a lot of physical space between the particles of a gas. Another one of their properties is that those particles have tremendous energy. Remember we talked about when you add energy to a system, particles, they gain energy, they move farther apart, and those particles are in constant motion. And because of these 3 properties, that means that particles have a tendency to completely fill whatever container they are in. So if I have a round container, I've got a round-shaped gas. If I have a square container, I have a square-shaped gas. So if I have this container and it's sealed, and I've got a gas inside of that container, then the particles which make up that container, eventually they will collide with the walls of their container. So eventually those particles, because of these three properties, they have a lot of energy, they're always moving. Eventually they're going to collide with the walls of their container. And when they do that, they're going to exert a force on the inside surface of that container. And that force is what we call pressure. That's what we call the pressure of a gas, that is the force that they exert on the inside walls of their container. Now we can compare that with another type of pressure called atmospheric pressure. So let's say that this is the Earth, okay. And then above the Earth, you have all these molecules that constitute the atmosphere. Okay. You have all these particles that constitute the atmosphere. And our atmosphere is mostly nitrogen gas, but there is a lot of water. There's also a little bit of carbon dioxide. There's some oxygen, plus a ton of other gases like ozone, natural, methane, et cetera, et cetera. There's argon gas. There's all kinds of gases which constitute our atmosphere. But the major component of our atmosphere is mostly nitrogen. So you have all these molecules that are suspended above the Earth's surface. Well, you know that Earth exerts gravity on everything that is on its surface. Gravity is also exerted on the individual particles themselves. So out here in the atmosphere, all these different gases, gravity is pulling them towards the Earth's surface. That's what gives us our atmosphere. That's why oxygen stays close to the Earth's surface. That's why nitrogen stays close to the Earth's surface, is because gravity is literally pulling these molecules towards the Earth's surface. Well, eventually those particles are going to hit the Earth's surface and they're going to exert a force just like if they were on a container. So due to gravity, the atmospheric gases will eventually strike the Earth's surface and exert a force against the Earth's surface. So that force of the gases striking the Earth's surface and bouncing off, that's what we refer to as atmospheric pressure. So two types of pressure that I'm relating, they're both a force, okay? They're both a force. And they're both a force that results from striking the surface of something. But when we talk about gas pressure, we're talking about like a container of gas. But if we're talking about atmospheric pressure, then we're talking about literally the air around us striking the surface of our desks, striking the surface of our cars, striking the surface of the earth due to the action of gravity. So because we're measuring pressure in two different places, we have different instruments which measure these types of pressure. Atmospheric pressure is measured with an instrument called a barometer. And I'll show you a picture of an old school barometer, but atmospheric pressure is measured with a barometer. Other gases inside of a container are measured with a manometer. So a big difference. When we are measuring atmospheric pressure, we always use a barometer. Any other gas, we use what's called a manometer. Sometimes people just call it a pressure gauge. If you've ever measured the tire pressure, you know how much air is inside of your tires of your car, that little device that you use. A lot of people say, oh, somebody get me a gas pressure gauge. It's actually called a manometer. That's its real name. If you are measuring the fluid in a system, like if you're measuring blood pressure or if you're measuring the pressure of water moving through tubes, you're using a different instrument. You're using a sphygmomanometer. That's measuring the fluid in a system. So let me show you a picture of a manometer, or excuse me, a barometer. Here's a picture of a barometer. This is a famous barometer that was actually designed by, you guessed it, Amedeo Avogadro. He actually designed this instrument right here in order to measure the pressure of the atmosphere. And I'll show you how this works. What he did was he took a large test tube, I mean a really long test tube, about 4 feet in length. He took a really long test tube and he filled it all the way to the tippy top with mercury. So if I draw a picture for you, that might be a little easier. So Amedeo Avogadro, he took a long test tube, about 3.5 feet, and he filled that test tube completely with mercury. Remember, that is a liquid metal. Okay, he filled it all the way to the tippy top with mercury. And then he turned it upside down inside of a dish. Turned it upside down inside of a dish, and that allowed the mercury to flow out. The part where there was no mercury, that left behind a vacuum. And so now you have mercury flowing out into the dish. And so what he did was he took this device, which he referred to as a barometer. He took this device all over the place. He took it all over the place. And so he would take it like on top of a mountain. He would take it to sea level. He would take it to places that were below sea level. And he would make observations about the column of mercury inside of the test tube. And one thing he noticed was that when he was at sea level, here's his mercury. Then the column of mercury was approximately 76 centimeters. That was the column of mercury. So if he measured it right here, that was approximately 76 millimeters. My picture's not so great, so I'll show you on the diagram. I'll show you on the diagram. So here's the diagram. Here is the dish. Here is the long test tube that he had filled full of mercury. He flipped it upside down, and when he did that, some of the mercury flowed out into the dish, leaving a space or a vacuum at the top. And when he would take this device to sea level, he noticed that inside of the column, inside of that test tube, the column would always rise to 76 centimeters. And so he decided that the reason that that column was 76 centimeters was because right here, the atmosphere, literally the gases that make up the air around us, were pressing down on the column of mercury. When they would press down on the mercury in the dish, then the mercury would go up and it would rise inside of this column. And so the pressure was enough force to make the mercury rise 76 centimeters, which is about almost 3 feet up inside of this test tube. So he referred to that as a standard atmosphere. This is where Amedeo Avogadro began to kind of quantify how much pressure is actually in the atmosphere. So we refer to 76 centimeters of mercury as being equivalent to 1 standard atmosphere of pressure. That's a definition. Okay, that's a definition. 1 standard atmosphere's pressure is equivalent to 76 millimeters of mercury. A lot of times we measure, and this is what we call 1 ATM, by the way, 1 atmosphere of pressure. So 1 atmosphere of pressure, another way to write this, is 76 centimeters of mercury. That is also equivalent to 760 millimeters of mercury. That is also equivalent to 760 torrs. Oh my goodness, I just realized I told you the wrong name. It was not Amedeo Avogadro that did this. I got my scientists mixed up. My mistake. It was not Avogadro that did this. It was Evangelista Torricelli. Evangelista Torricelli. And so change that in your notes. Avogadro did not invent the barometer. It was invented by Evangelista Torricelli. He's the one that invented the barometer. My mistake. But this is still important, is the quantification of a standard atmosphere is equivalent to either 76 millimeters of mercury, 760 millimeters of mercury, or 760 torrs, named after, of course, Evangelista Torricelli. So when we measure pressure, we're going to be measuring them mostly in millimeters of mercury or 760 torrs or in atmospheres. That's how we measure atmospheric pressure. Now there's a relationship that we're going to examine between the pressure of a gas, the volume of a gas, the temperature of the gas, and the number of moles. These 4 things, pressure, volume, temperature, and moles, these are all going to be related by the gas laws that I'm going to list for you. Okay. So we're going to be worried very much about pressure, volume, temperature, and moles. When we talk about the pressure of a gas, we're going to be almost always relating it in atmospheres. Volume is going to be in liters. Temperature is going to be in kelvins. And moles is just going to be in moles. Okay. Moles is just going to be in moles. So I said at the beginning I had an ambitious schedule for today. Let's see how many gas laws I can actually share with you. So the first gas law is known as Boyle's law. Named after Robert Boyle. And we most commonly see it written like this. There's different ways that you can express it, but it's most commonly expressed like this. Most commonly expressed like this. P1 V1 is equal to P2 V2. This is only true assuming that temperature and number of moles doesn't change. In other words, temperature and number of moles are constant. That means that they don't change. And so what the gas law says in words is that pressure of a gas is indirectly proportional to the volume of a gas. So when you increase the pressure, the volume decreases. So the pressure of a gas is indirectly proportional to the volume of a gas. So pressure and volume are indirectly proportional. And this kind of makes sense if you think about it, because if you have a container and you've got all these gas particles inside of your container, and let's say the lid of your container is more like a piston, it's a movable lid. Okay. Here's the lid of your container. Okay. Let's say you have 1 liter of gas and it's being held at 1 atmosphere, okay? 1 atmosphere pressure. Well, what if I take this lid and I push it down? So now my container is no longer 1 liter, but maybe I've cut it in half. So now here's the lid of my container, but I still have the same number of gas molecules. They're just taking up half the space. Now I've got half a liter. And this, we'll say this is at 0 kelvins, and this is at 0 kelvins. Well, if I reduce the size of the container, then my molecules are going to be hitting the inside of the container more often and with greater force. So probably, not probably, but my pressure will increase proportionately to the amount that I have decreased the volume. Chances are this is going to double. Because if I still have 1 mole of gas, and the only thing that changes between these two is the size of my container, then something has to give in order to keep conditions sort of like at a homeostasis, if you will. So if I change the size of the container, I make it smaller, then the pressure is going to have to increase. And that's what Boyle's law is saying, is that the pressure and the volume of a gas, they're indirect. When one goes up, the other one goes down. This is only true if the number of moles and the temperature is kept constant. Okay. Now we'll compare that with Charles's law. We'll compare that with Charles's law. Charles's law, there's more than one version, but the most common version that we see relates volume and temperature. V1 over T1 is equal to V2 over T2. This is true if pressure and number of moles are constant. Okay, if pressure and number of moles are constant. meaning that we don't change the pressure and we don't add or take away any gas. But in this version of the gas law, it says that the volume of a gas and the temperature, and this of course is the Kelvin temperature, are directly proportional. So if one goes up, the other one goes up. But this has to be in kelvins. Okay, the Kelvin temperature. Gay-Lussac's law, or sometimes it's referred to as another version of Charles's law, and your book puts these together. So I'll put them together. But Gay-Lussac's law, which is kind of another version of this, relates pressure and temperature. That says the pressure and the temperature are related like this. This is only true if volume and number of moles don't change. So whatever's missing from the equation, remember pressure, volume, number of moles, and temperature, whatever's missing from the equation, that's what we keep constant. And this says that the pressure of a gas is directly proportional to the temperature of the gas. So if one goes up, the other goes up. If one goes down, then the other goes down. And of course, this is the Kelvin temperature. So these two you can kind of reason with also if you think about, you know, what a chamber would look like. And I have a diagram to show you for Charles's law. What a diagram would look like, kind of like what we drew over here, relating pressure and volume. Okay. Go ahead and type in the chat window a number 1 for me when I can switch to my diagram. All right, I'm getting a lot of number 1s from everybody, so I'm going to go ahead and switch to the diagram. And by the way, I'll share these diagrams with you. I'll share these diagrams with you. Oh, let me try that again. Okay. So here's an example of Charles's law. Make this a little bit bigger. Okay. So here's a nice diagram of Charles's law. So when we look at this one, in the top row, this is Boyle's law, which is kind of what we diagrammed a while ago. This is Boyle's law, and the bottom two are Charles's law. But I'll review this one for you. If we start out in the middle here with Boyle's law, here's a certain amount of gas. Here's our container, and this is the lid our container, and the lid can slide up and down. If you notice the pressure gauge here at the top, this is where we're starting. Remember that Boyle's law relates pressure and volume. So when one goes up, the other goes down. If you release the pressure, or I'm sorry, if you change the volume so that the volume increases, so if I move this up, if I move that up, notice that the pressure gauge decreases. That's because now I have more space for the molecules to move around, and they're not going to come into contact with the walls of their container as often or as forcefully. So if the volume increases, the pressure decreases. Vice versa, if I start out here in the middle on my Boyle's law, and like we did in our diagram, I make the volume smaller. If I decrease the volume, then notice my pressure gauge. My pressure is going to increase because I have less space for these guys to move around. They're going to collide with the walls of their container more often and with greater force. And this is all assuming that the temperature never changes. Boyle's law assumes that the temperature never changes, and I never add gas and I never take any gas away. Looking at the middle diagram, this is volume and temperature. Okay, this is volume and temperature. So starting out in the middle, okay, I have a certain amount of gas. If I increase the temperature, if I add energy, then my molecules are going to move around faster and more often, and they're going to want to spread out. So the pressure, in order for it to stay the same, I'm going to have to increase the volume. Remember that pressure is constant. All I'm changing is the Kelvin temperature. So if I don't want the pressure to change, I'm going to have to give these guys more room to move around to accommodate their extra energy. Vice versa, if I'm starting out again in the middle and I lower the temperature, I take away energy, then if I want the pressure to remain the same, I'm going to have to reduce the volume so that they continue to collide with the walls of their container as often with the same intensity as they did at a higher temperature. So Charles's law is assuming that we keep the pressure the same. Notice that the pressure gauge is the same in all of them. All we're manipulating is the temperature and the volume. We're also not changing how much gas that you have inside of the container. Gay-Lussac's law, or the other version of Charles's law, this one relates pressure and temperature. So on all of these, notice what is not changing is the volume. See how the level of the lid stays the same every time? So volume is remaining constant. We're also not changing how much gas we have inside of the container. That's always constant. But what we are changing is the temperature. We are changing the temperature. So notice that when we lower the temperature, the pressure changes. Remember, taking away energy is the same thing as lowering temperature. So these particles are going to hit the walls of the container less often and with less force. But if we go the other direction and we have a higher temperature, again, we don't change the volume, our particles are going to become more energetic, and they're going to hit the walls of the container more often and with greater force. Let's practice some math problems with these various laws. But I promise you, the mathematical versions that you're going to see, most often of these laws are the ones, are the ones that I have written here. Boyle's law like this, and the two versions of Charles's law like that. Those are what you're going to see most often. So let's practice with these. I had oh, nope, wrong one. So we'll look at your textbook. If you have your textbook handy, we'll practice some of these out of your textbook. I'm looking at page 216 through 217 at the end of your textbook. And I'm looking at number 5.19. So if you have your textbook and you want to follow along, I'm looking at number 519 at the end of your textbook. The text is a little small, so I'll rewrite the question. Number 519, it says you've got a gas that occupies a volume of 725 mils at a pressure of just under 1 atmosphere. And then it is allowed to expand at constant temperature until the pressure reaches 0.541 atmospheres. What is the final volume? Okay, what is the final volume? So when you look at these word problems, which everybody cries when they see them, let me show you a strategy that I do. Here's a strategy, is I go through and I try to identify, before I even decide what gas law I'm going to be using, I identify all my variables. So I see right here I've got a volume of 725 mils, so that's going to be a volume. Here is a pressure amount. And then see this constant temperature. So that means that temperature is not going to be changing. And then I've got a pressure that reaches 500 or 0.541 atmospheres. Well, because of the way the problem is worded, that means that I'm going to end up here and I'm going to start right there. If it's asking me for the final volume, I'm looking for V2, the second volume. So what must be given to me is volume 1. So identifying your variables inside of the problem, sometimes that can be the most challenging, but the most useful thing that you can do. Once you identify your variables, then you can go back to your notes and say, oh, I know which one this is going to be. This is going to be a Boyle's law problem because I've got pressure, volume, and the temperature is constant. So I'm going to be using P1, V1 is equal to P2, V2 to solve this one. Now, this is just preference. Okay, this is Mrs. Weir, what I like to do. I like to go ahead and solve the problem for V2 before I substitute. So using my mad algebra skills, I know that P1 V1 over P2 is going to be the version that I'm going to use, because now it's solved for V2, and now I can just substitute into the problem. So pressure 1 is 0.970 atmospheres. Volume 1 is 0.725 liters. Pressure 2 is 0.541 atmospheres. Now I can just do my math. And I end up with 1.30 liters. Check my math. Give me a shout out if I did my math incorrect.
Shouldn't it be milliliters?
No, I converted to liters.
Oh, okay.
But if you didn't convert, it would be 1,300 milliliters. Get in the habit, Martine, of putting this always in liters. It'll save you headaches later.
All right.
right, let's try another one. In your, I'll wait, give me a number 1. If I can move on, I want to try one more. All right, I'm gonna try now also on the same area. I'm going to do number 5.24. And I'll write this one out. And it says, under constant pressure conditions. I love that. Under constant pressure conditions, a sample of hydrogen gas initially at 88 degrees Celsius and 9.6 liters is cooled until its final volume is 3.4 liters. What is the final temperature? Okay, what is the final temperature? So let's do the same strategy. This is nice under constant pressure because that's going to help us figure out which gas law to use also. But we've got a temperature here and we're looking for the final temperature. So it looks like I'm looking for T2. This must be T1. Final volume, well, that's V2. This must be V1. So now I need something that relates temperature and volume and under constant pressure. And so if I go back to my notes, that looks like a Charles's law problem to me. Going back to my notes, that looks like the Charles law problem. So I'm going to be using V1, T1 is equal to V2 over T2. But remember that your temperature must be in kelvins. So go ahead and convert that right away. Because if you put it in Celsius, you won't get the right answer. So 361.15 K is our temperature. All right, so looks like I'm solving for the final temperature. I'm solving for T2. So using my mad algebra skills, T2 is going to be equal to V2 T1 over V1. If you don't like to do this, you can substitute first and then solve for T2. Does not matter, whatever you prefer. I like to do it this way so that when I substitute, it's easier for me to substitute this way. But my second volume is 3.4 liters times the temperature in kelvins over So you can check your math with mine. So here's what I recommend that you look at between now and Wednesday to get prepared for the in-class quiz. Look at your review questions, and these are at the end of the chapter. Pages 216 to 217. Look at numbers 5.15 to 5.26. Those will be very helpful for you to get prepared for Wednesday. Any questions? So on Wednesday, make sure that you bring your calculators and your periodic tables. We're going to need them. We're going to do the 2 more gas laws, and then we're going to introduce some stoichiometry. So I will prepare you now. Math is going to be a big part of our lecture on Wednesday. So we'll have plenty of time to exercise our math skills on Wednesday. Yeah. Do you have any questions for me?
I have a question.
Go ahead, Dimitri.
It's about the complete ionic or the net ionic equation. I was wondering if you could do another one of those for me.
Sure. Before I take this off and I answer Dimitri's question, did anybody have any other questions on the gas laws?
I have a question about the quiz that we took, or it's kind of revolving around the ionic equations.
Okay.
It just where it says for all of them, you know how it says to answers must include the physical state abbreviations. On the first ones, it says like solid aluminum, solid magnesium. So is that you giving us part of the answer, or is that, or
Yes.
yeah, that's you giving us part of it, right? We're supposed to solve the other part.
Yes. Using your solubility chart.
Okay, cool. That's the only question I had.
Okay. Dimitri, can you be more specific? Which one are you working on?
I've got the complete ionic equation, but not the net because I don't know how to do it. But
Oh, okay.
let's do like 8 or something. Or no, 8 is no reaction. So
Okay.
I mean,
It's easy.
no, it's not. You didn't hear that. But let's do 9.
Can you read it to me?
Oh, my bad. Do you want it balanced too?
Sure.
Okay, 3 calcium OH2 plus iron 3 chloride 3 yields 3 calcium chloride 2, or just calcium chloride. Okay, and 2 iron 3 OH3.
Okay. So this is your solid. This is aqueous. This is aqueous. And this is aqueous, right?
Yes, that's what I got.
Okay. So on your net ionic equation, spectators are aqueous on both sides of the arrow. So you'll have to eliminate the spectators. So if you're looking at your ionic equation, you should see that you've got something like, you'll have calcium on both sides. Like you'll have calcium over here. And then on the other side, you're going to have calcium over here also, aqueous. If they are aqueous on both sides of the equation, then they are spectators, and they do not take part in the reaction. Or your complete ionic. Your net ionic contains participatory ones only. Okay, so your net ionic, to go from your complete ionic to your net ionic, eliminate the spectators. So I'll show you what I mean. I write it out. You've got calcium. This will be unbalanced, but
With the iron, it has two. The iron chloride. It's weird.
hold on.
Okay. Oh, you're doing it unbalanced. My bad.
Yeah, I'm doing the unbalanced. So these are all aqueous, right? And this one's solid. I know it's unbalanced, but that's okay. This should be what your complete ionic looks like.
Yeah.
Okay. So the spectators are going to be the ones that are aqueous on both sides. So this is a spectator. This is a spectator. That's a spectator, and that's a spectator. Okay. They don't participate. They're not participating. So we'll X them out. They are spectators. The participatory ones are the ones that you have left. So to get your net ionic equation, you simply copy who's left. So iron plus the hydroxide ion the solid. Of course, this would have to be. There you go.
Okay.
Yeah, you eliminate the spectators in order to get the net ionic, because this is the real equation. These guys are just hanging out. They're not actually doing anything. The real equation is what you have left over once you eliminate all of the spectators.
Wait, so you moved it was OH3, but you moved the 3 in front of the OH?
In order to balance it.
Oh, all right. Again.
In order to balance it.
Okay. All right.
I didn't move this 3. That's just so I can balance it at the end.
Yeah. Is it better to just leave the equation unbalanced?
No,
No?
not.
Or like before you do it?
Oh, yeah, it doesn't matter up here. It doesn't matter. Your equation should always be balanced.
All right. And my last question is, what is a redox reaction?
The redox reaction, that's the one where you have a transfer of electrons.
Oh,
That's
yeah.
not something I can answer in 2 minutes.
It's not? Okay.
No, I can't answer it in 2 minutes.
All right.
Okay, this is weird. So
Yes.
would most of them, if not all, be a redox reaction, because we're basically doing like a switch of
Oh.
like.
Hold on, Mary, just a second. I'm actually over time. Okay, I'm over time, so I'm going to stop recording. Over time,